this, but you know, I mean, I'm heading a phase, you know, by motivating the experiment. Okay? So, you know, I have these, and by the way, this was an homework some time ago. I don't remember which year. So 2 years ago, 3 years ago. Okay, but you know. So anyway, so when you have a car, and it's black. So when you have a car, you know, the car is approaching with a specific speed v. So now imagine that here you have a radio frequency or a device. Okay. The telecom knows it's a sort of radar, no. So it doesn't matter. So you have a device. And this device is transmitting a signal here. The signal bounces back because of the metallic surface. Okay? So the signal is, in jargon, is called backscatter. It was backscatter, okay? And so you have this signal that is backscatter. Now, if you transmit a g of t, you get back a g of t minus tau. And tau depends on the distance. Let me call distance d. Okay? So now tau depends on the distance. Easy. Now, you know, my goal is not to look at this, or is also to look at this. Right? So, you know, I'm looking two sides of this problem. Okay. Now, the problem I'm looking is the following. Problem number one. G of t is equal to a sinusoid. So it's a cosine omega 0 t plus a certain phase. So this is what I'm transmitting. Now, if the vehicle has a specific speed v, the signal that I get back, okay, so what I measured, x of t, is equal to an amplitude, then a cosine of omega hat t plus a certain phi prime, which is different from the previous one, plus wt. Okay? So what I measure, you know, I measure omega hat, which is different from omega 0 because of the so-called Doppler effect. Okay? So, an omega 0, omega hat is equal, now I get the formula because I don't want to reinvent again. Yeah. Is equal to omega 0 multiplied by 1 minus 2 times the speed of the vehicle divided by c. C is the propagation speed of the electromagnetic wave. Okay? So now, you know, this is c. This is 3 times 10 to the power 8 meter per second. Okay? This is the propagation of the electromagnetic waves. And v is the speed of the vehicle. Okay? Whatever it is. Now, you know, my goal, okay, and everything depends on omega 0. So, you know, everything is related to omega 0. Okay? No, so good. So, you know, that means that to estimate the speed, I need to estimate the frequency. Actually, when I need to estimate the speed, I need to estimate the frequency shift, actually. This is the way how it's called in jargon. It is called frequency shift because when you get the backscatter echo, you got the signal coming from the vehicle that is moving, and then you have all the signal coming from the surrounding, which since the surrounding is static, there is no Doppler shift. So only the vehicle is shifting in Doppler. The others remain there because, you know, for the environment, okay, v equals 0, and then, you know, omega hat is equal to omega 0 for the environment. But for a vehicle that is approaching to the police, you know, which is pointing there, and in that case, you know, omega is different from omega 0. So what I expect overall, you know, is that I receive something that is a big signal which is the frequency omega 0. And then, you know, it's a different, it's another signal which has a lower frequency. You know, the reason is like a train. When you're in a train, you see you have a, you see, is a lower frequency, right? Okay. And then, you know, this is my omega naught, okay? So my goal is to get the signal, the frequency of omega naught. Because, you know, I estimate that one, and then, you know, from that one, I can estimate V. And then I give a ticket. Okay? Fine. If it is larger than, you know, 50 kilometers per hour or so. No. But, you know, I mean, since every time you make a ticket, you need to keep the uncertainty. Okay? Because the uncertainty is where the lawyers can try to avoid the ticket, right? Okay, so you go to a lawyer, and then, you know, but when you go to a lawyer, usually, you know, since you are more serious, you don't go to the lawyers. Perhaps you don't get the ticket, but, you know, if you get the ticket, and the lawyer says, perhaps, you know, I mean, this goes within the uncertainty of the tolerance of the system. Now, what we are going to derive is the tolerance of the system. Okay? The minimum tolerance. Now, so let's make the problem, you know, I'm putting the problem more and more precise. Yeah? So let's say that for some magic reason that the radar people knows, okay, which is clutter removal. But so for some magic reason, this one, the clutter, is equal to 0. Okay, the environment, which is called clutter, is, you know, is a sinusoid which remains there. We are interested to the other one. Okay, now we might face a problem of resolution. You see, because I have a big sinusoid and a smaller one. You know, sometimes perhaps I don't see the smaller one if I have a big one. Okay, let's neglect for this problem. We will look at this later. Now, so my, you know, my simplified problem goes like that. So this is my data. So there is no clutter. Okay? So let's make an example. Let's assume that a squared divided by 2, then multiply by the power of the noise. Okay? This is equal to 20 dB, 10 dB, 10 dB. Let's make it 10 dB. Okay. So what is 10 dB? Let's discuss with our friend that doesn't know what is the dB. Okay, that means that, you know, this ratio, okay, is evaluated logarithmic scale. So that means that, you know, we have a 10 times logarithmic of base 10 of this one is equal to 10 dB. So, you know, sometimes in order to indicate that this measurement is in dB, what I say, I put in a square bracket, okay, and then I say a squared divided by 2 times sigma w is equal to 10 dB. When I put in a square bracket means I converted in dB. I apply the logarithm. Okay? So this is a specification of the system. Okay? So this depends on the specific system. So 10 dB is because of what I'm buying. I'm buying a system that has 10 dB. Okay? So for that specific setting, I'm applying to 10 dB. Now, my goal is to evaluate the speed such that the uncertainty, okay, is 1 meter per second. Okay? So it's just an invented number. Huh? Okay. So I did not prepare this exercise put in this way. So, you know, just for me, so you see how the problem is built. So that's better. Now, so, you know, I have that the uncertainty on the speed. What does it mean? It means that, you know, v hat minus v, okay, you know, this one should be approximately within 1 meter per second. Okay? This is the degree of uncertainty. Now, this quantity makes 10.
What is it, 10 dB? What does it?
Oh, it's that measurement. So, in this way, if I say that this is equal to 10 dB, I know what is A squared divided by 2 sigma squared. Okay? That, by the way, in this case is equal to 10. Okay? So let's make it more esoteric. 30. Okay? So that means that, once I know this, I know that A squared divided by 2 sigma W squared is equal to 20. Okay? So when I assign in dB, it's like to assign in normal scale, linear scale. This is only to make the telecom and electronics happy, okay? Because they treat logarithmic every day. They think in logarithm. Okay? They think in logarithmic is because since they didn't do a lot of multiplication, since in the early stage, the electronics and telecom, they use a lot of a device which was called the regular. Okay? Since the regular makes the multiplication by summing segments, for that reason we use the dB. But if I make an exercise, I give you 20. Don't be afraid. I don't give you 30. Okay, so just to make the presentation more complete. So let's assume that my error should be 1 meter per second. So, but put it this way, we cannot do that much. So now let's evolve on that. So we can say that my error V minus V hat, okay, is behaving as normal, zero mean and a certain variance of the error, which means that I am assuming that the estimator is unbiased. Okay, so assume that I'm operating in the best condition. My estimator is unbiased. Okay, so if I say that this is the error, so this means that the error has a certain distribution. This is V minus V hat. Okay, so the error has a certain distribution with a certain standard deviation, which is sigma V. Okay. Then I can say that I can tolerate. So I can, let me say, somewhat arbitrarily decide that, I want that my 1 meter per second is guaranteed by a certain probability, which means this area gives me the probability that any of the random generated process, which is the random generated variable, which is the estimated value, falls within this interval. Okay? So, things about that, I can assume that this probability is, 99.99, and then, according to that, this interval is equal to 2 times 3 sigma d. So, since my error is 1 meter per second, so this total interval is 2 meters per second. So I need to write that 2 meters per second should be equal to 6 sigma d. Then according to that, I get a sigma d, which is 1/3 meter per second. So if I make my experiment, then what I want is that my accuracy should be better than 1/3 meter per second. Better means smaller. Okay? So the requirement is that the sigma v should be smaller or equal than 1/3 meter per second. So this one, this 1/3 meter per second is the upper bound. Okay? Now, so you know what I'm doing now is I want to see how many samples do I need to make the acquisition of the signal to comply this specification, assuming that I'm using a perfect estimator. Okay? So, because my system is acquiring the data, so I'm shooting a sinusoid, the sinusoid comes back, with a Doppler effect. My processor unit is taking these shifted sinusoid, is applying a magic processing, which is cutting out all the Doppler effect, or the clutter effect. I have only one sinusoid, so what I need to do, I need to estimate the frequency of a sinusoid in white noise. I'm assuming that the noise is white, blah, 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 okay? So, now for instance, how can I map, because here I have the tolerance on speed, and on the other hand, I have a frequency, omega bar, okay? So, how can I map, one requirement onto the other? Now, to map the requirement one onto the other, what I need to do is the following. So, I need to evaluate the variance of omega naught. Okay? So, let's take that in this relationship. So, let me copy it again. So, what I need to calculate? I need to calculate the variance of omega naught. And the variance of omega naught is omega 0 squared. Then it is the variance of 1 minus 2 V divided by C. Okay? So, 1 is a deterministic quantity. And so the variance is 0 for that. So the only variance that matters is the second term. So I have omega 0 squared. It is 2 is the square is multiplied by 4 divided by C squared. And then is the variance of the speed. Okay. So that one, this is the variance of the speed. So once I get the variance of omega, I have the variance of the speed. So it's just a mapping. Okay? So I don't know, we need to set some numbers. Now, so imagine that omega 0 is, let's make not in radio frequency, millimeter wave. So let's assume that omega 0 is 2 pi multiplied by, let's make it 1 megahertz to make it simple, okay? Which is not realistic as a radar, but it's to make the exercise easy, okay? So it's 10 to the power 6, okay, megahertz, and C is 2 is 3 times 10 to the power 8 meters per second. And this is second. So let me put together, okay, so the variance of, let's say, yeah, it's okay. So the variance of omega naught is equal to 4 pi, then it is 4, look at here. I have 2 pi, and then it goes 2 pi here, I have 4, so it is 2 times 2 is 4, 4 is 16, so it's 16, so this is 16 pi square, and then omega is 10 to the power 6, and on the other hand I have 3 mix 9, 10 to the power of 16. Okay. And that one is the variance of the speed, which is 1, 9. Okay. So that one is 16 pi squared 81, so it's 16 pi squared, then it is 81, then it is 10 to the minus 10. Okay? This is the accuracy I need.
Power 2. 10 to the 12, not 10 to the 6, I guess.
Which one?
10 to the 6. It should be 10 to the 12.
Right. Thanks. 12 was 16 and minus 4. Okay, now makes more sense. It was too big. That was more. Okay. So, you know, this is the accuracy, okay, that is required by the system. Now, you know, we remember what was the signal-to-noise ratio. Now we need to see how is the estimator. So my goal is the following, so that you know what I'm going to prove now. Is it clear here? This is a practical engineering problem, okay? Engineering for me makes no sense. Engineering means you use numbers, okay? So if you don't use numbers, you know, you are talking about nothing. So, my specification now is this one, okay? So if you like in hertz rather than, you know, in radian per second, okay? So let me say here, so the variance of frequency, no. So I take everything divided by 4 pi square. So it is 4 divided by 81, 10 to the minus 4. Okay, so this is the variance of frequency. So my new problem is the following. So what I expected to see is this one. Now, I know what is known. It is known that a squared divided by 2 times sigma squared w is equal to 20, right? Okay, that is 20. And I know that the variance of the frequency should be smaller than equal than that. Okay, because that one is to avoid to have a legal issue. So the variance on the frequency is so 4 to 81. 81 is like 80. Okay, so 80 then is 20. So it's 1 over 20. Okay, so 1 over 20, 10 to the minus 4. So it is 1/2, 10 to the minus 5. Okay, so it's 1/2 is 10 to the minus 5, okay? So the variance should be smaller than 10 to the minus 5 divided by 2, okay? This is what I want. Now, what is not known is how long or how many samples should I process. Okay. No, because I mean, if you remember, the frequency estimator is taking a vector of samples and then making the projector, blah 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 blah, and then according to that, I mean, I need to collect a certain number of samples. So what is not known is the number of samples. Okay? Actually, the number of samples are related, okay, to the sampling interval, which is not specified now. So, but in any case, okay, so this is a practical, here is Hertz squared. Remember the dimension, huh? Variance of frequency is Hertz squared, variance of length is a meter squared, okay? Variance of time is a second squared, and so it's variance. So, I mean, the problem says that in this setting, here I have the variance of the estimated frequency. And so, and then I can calculate the Kramer album on that. So, I mean, the specification says I want to add my variance lower than 10 to the power 5 divided by 2. Hertz squared. Is it clear what the problem is telling to me? Okay. I derive this number 10 to the power 5 divided by 2. Okay, it's by physical consideration. There's no engineering from my point of view. It's just stupid physics with the Doppler and so on. Okay. So right now, that means that if I have my estimator, okay, and for instance, I can calculate the Kramer bound, just to say something, okay? So imagine now that the Kramer bound is going this way. This is the Kramer bound. So why should I use the Kramer bound? Because from the Kramer bound, I know that reading from here, okay, this is the minimum. Okay, the minimum. Because you know, I mean, in my system, since my error should be smaller than that, that means that from the Kramer bound, so since the Kramer bound is assuming that I'm using a perfect estimator, since the Kramer bound is assuming that is the most efficient estimator, then you know everything says that from the Kramer bound, the number of samples that I need to use should be larger than a specific minimum. Okay? Now, I mean, what I want to do now is to derive the Kramer bound in this case. And you know, and you are motivated to look at the problem, and you will do it by yourself. You put it together, okay, the Kramer bound that we find by the sample analysis with the physical problem. I'm not doing that. You will do, and then you will tell me. Okay? So let's make the next step. Okay. So you know, we need that one. By the way, I want that you know everything is kind of clear. The Kramer bound is telling to me that there is no estimator that is going better than that. So since you know there is no estimator, so I can imagine that my particular estimator is going this way. Okay, this is the actual estimator. So since if the actual estimator is this, then you know this is the true and minimum. Okay? Because that true and minimum is the minimum number of samples that you need to implement for the true estimator. Then I mean assume that you know you have another estimator, and this other estimator is making more processing. But at the same time, you know, this new estimator gets a better performance, is more efficient than the other. Okay, good, then you know what this means, that I'm using a lower number of samples. So now, you know, the trade-off stays in the middle, and it's something that you need to find, to disclose by yourself. It depends on the problem and so on and so on and so on. Okay? So, by the way, keep in mind that as engineers, you will be very often asked to give an evaluation to something, I mean, at the first order. Now, the first order is very strange. That means that, you know, sometimes you are asked to give an opinion kind of quickly. And so, if you need to give an opinion about the specific business system very quickly, then you can say, that, you know, I mean, this is the minimum number of samples. No question about that. Now, the minimum number of samples is impacting how much data I am collecting. So think about that if my data length is 3 seconds. So if my data length is the number of samples which corresponds to 3 seconds, let's make an hypothesis. So if my data is 3 seconds, that means that you need to ask to the policeman to be still, perfect still, that has not to tremble, because trembling is adding uncertainties, right? So that police has to be perfectly still for 3 seconds. You know, and if the car is fast enough, then you know in 3 seconds, it's gone. You are too fast, you know, you have a Ferrari, you have no time to catch it. Okay, so 3 seconds is not enough. So you see, so you need to have a very quick analysis of, I mean, if this min is enough, makes sense for the problem. If it comes 20 samples, probably, you know, I mean, you can, 20 samples, if a sample to whatever frequency, you imagine that, you know, you are asking that you need to collect at minimum 100 milliseconds of data. Well, you can ask the policeman to be still for 100 milliseconds. You cannot ask the policeman to be still for 3 seconds, you know. Try yourself. I mean, perhaps you are younger, but you know, you need to be still. But you need to be still, and if you make this movement, you are changing the Doppler. Because the Doppler depends on the propagation along the direction which is connecting the device and the vehicle or whatever. Okay? So, I mean, if you tremble in this way, Doppler doesn't change. If you tremble the other way, Doppler is changing. Okay? So, I mean, just some comments. So, I mean, you know, as I always say, I'm not giving any method. I'm giving a box with tools that you need to pick up depending on the application to solve the specific problem. Because every specific problem has a specific solution. Now, let's see how to process this kind of problem. So first of all, you know, our problem sample, okay, will be reduced to that. And this is from the book, from the SSP V2 book, okay? So this is from SSP V2, okay, PDF. So you have it, exactly that. So, you know, I mean, I've studied the maximum likelihood of frequency estimation, and I remember that it's very complicated because I need to calculate the projection matrix. So let's see how is this projection matrix. In the case I have a one sinusoid, perhaps you know it's not that terrible. So I mean I need to start back again. So I take the model. Okay, this is the model part, which is we already discussed. Okay, and then we have seen that the maximum likelihood method is by maximizing this one, and this is the projector. Okay, this is the projection onto the subspace of matrix of the columns of matrix H, and then I need to maximize that. Now, before this period, we need to take this formula and look at more seriously. Now, first of all, remember that H is characterized by cosine, a vector of all the cosine, and vector of all the sine. So let's work on this a little bit to see if something is getting, if it is getting better. Now, this is the slides we discussed here. Now, I need to do two parts. So I need to make, you know, I isolate this, the J omega in two parts. So I have X transpose H, and I have H transpose H to the -1, and then I have H transpose X. Okay, this is the metric that I need to calculate. So what I did, you know, I take the inner matrix multiplication, which gives me a matrix 2 by 2, and I calculate separately. And then I look at this one, and I calculate separately there. Okay. I don't look at this, because this one is the same as the other, except it's transposed. So now you know, I remember that H matrix is a block partition, so I have a cosine and sine. There's a matrix which contains, you know, all the cosine, all the sine. And these cosine and sine depends on the unknown frequency only. So since I have a block partition matrix, I can put together, you know, the computation of H transpose H in the block form, which means H transpose H is equal to cosine transpose sine transpose. Then I have cosine and sine. So this means that in the first position, I have cosine transpose of cosine goes here, cosine transpose of sine goes there, sine transpose of cosine goes there, sine transpose of sine goes there. Okay? So, you know, but what is cosine transpose cosine? Now, you know, if I look at this cosine transpose cosine, or, okay, we could look at first. So this one is a sum of cosine omega n, okay, square, and then is n going from 1 to capital N. By the way, capital N is our unknown in our problem, which is how much data I'm collecting, okay? So just to put you to the problem. Of the Doppler speed meter by police. Okay? Just to put you, okay, into the problem. So my unknown is n. So I analyze the problem in a general sense. So what is this cosine omega n squared? Now, you know, this cosine omega n squared, if I divide by n, this is the power of a sinusoid, cosine, okay, which is equal to 1/2. Now it is equal to 1/2 for n going to infinite. And it is equal to 1/2 if n, you know, is large enough, which means, you know, if I really need to see when the approximation holds, then, you know, I can perhaps look at it with a microscope. But, you know, at the beginning, for me, it's enough that n is larger than 2050. Okay? So if after my computation comes n equal 5, then I go back to my approximation, then it will be fine. Okay? Now, similarly, the same result is for sine squared, which is sine transpose sine. Now, cosine transpose sine, so it's a cosine and sine. So this is the inner product between cosine and sine. Now, the inner product between cosine and sine are orthogonal to each other. Now, the orthogonality is guaranteed for n going to infinity as well. Okay? So I'm assuming that n is always very large. Okay? Large enough. And then, you know, we got that this matrix, which was complicated at the beginning, is equal to n/2 along the diagonal and 0 on the off diagonal. This matrix now becomes easy to compute. It was a nightmare, and now it's becoming easy. Okay? Now the second one. What is H transpose omega? H transpose x. H transpose x is simply cosine transpose x and sine transpose x. Now, you know, this is the cosine transform and sine transform. So these are the elements of the Fourier transform. Because I'm taking the signal, projecting onto the cosine. Taking the signal and projecting onto the sine. So now when I put together, so I take this, put into there, take this, put into there, transpose. So what I get is that my cost function that I need to optimize is 2 divided by n. Remember, this 2 divided by n is n divided by 2 diagonal with identity, okay? So this one is equal to the minus 1 of the diagonal, okay? Then I have cosine transpose x squared plus a sine transpose x squared. Well, you know, this one here. Cosine xn cosine squared plus xn sine squared. Okay? So, you know, collecting the terms, this is equal to the this is equal to the Fourier transform absolute value to the square. So my metric to optimize is simply this. So I need to calculate the Fourier transform of the sample. So it's the max of Fourier transform of the samples like that. This is my estimator. Remember, it's a Fourier transform, not the discrete Fourier transform. Okay? is a subtle difference. Okay, here it is. So, you know, that's how the method for frequency estimation. Now, about frequency estimation, about the method for frequency estimation, we return with the specific exercises. Okay, using the Monte Carlo simulation to make a Monte Carlo simulation for sinusoids. Right now, I stop here. There is a some. Let me add a comment here. Okay, so there is computation needs some care, some practical care to be discussed at Monte Carlo analysis later on. Okay? So don't get crazy about that. It deserves care. If you do it wrong, you don't get the frequency of the sinusoid. But you know, I mean, let's assume for a moment that, you know, we have our friend that knows everything, how to do it. Okay? So he is the person that knows how to calculate the maximum there, blah, 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 blah. Perfect. Now, our goal, remember, was to get the Kramer out. So, I mean, what I need to calculate is the Kramer out now. So, I mean, what I need to go, I need to go back and I need to say, hey, how many parameters do I need to estimate? So my goal was to get the frequency, right? So since I need to estimate the frequency, then, you know, I write a set of parameters. So my set of parameters here, okay, are amplitude, frequency, frequency. Now, you know, technically, this and this are nuisance. Because I'm only interested into the phase. This is my, you know, my crucial parameter, the frequency. So phase and amplitude are nuisance parameters. Now, let's assume that, you know, in my model, I want to estimate O3. So what I need to do, I need to create a Fisher information matrix. Now, how is the Fisher information matrix? So the Fisher information matrix, in this specific case, okay, is a 3 by 3. So the Fisher information matrix contains all the terms which are relevant to calculate the Kramer-Hall bound. Now, so let's see which Fisher information matrix I call A. Okay. So let's see which one. So my Fisher information matrix, I need the term along the diagonal, which is the Fisher information matrix computed for the amplitude. In the second position, because omega is the second position, amplitude, omega, phase. Okay? They are in this way. In the same order. Now the ordering of Fisher information matrix is crucial. If you make a mistake on ordering, you don't get anything. Now, in the second position, I have the Fisher information matrix between amplitude and omega. And the third position, I have a Fisher information matrix between amplitude and phase. Then here I have a Fisher information matrix between amplitude and omega. It's the same because the matrix is symmetric. Here I have the Fisher information matrix of omega. And here I have omega phase. Here is the same as the previous one, so which is A phi. Here is the same as the other, omega phi. Here I have the efficient information management phase. I need to compute all this one. So the number of independent computation is 1, 2, 3, 4, 5, 6. No question on that. You need to compute all 6. Okay. So now a little bit of care. Now we go back to the formula, which is, since it's written in our back of the book, of the exam, and this problem is framed into that one. Now, the problem says, okay, so CW, what is CW? CW is sigma squared W, multiplied by the identity. White is noise is white. Perfect. So, in that specific relationship, that sigma W does not constitute a real issue. Now, I have the multiplication of different terms. Okay? So, with a little bit of care, I need to compute this term. So, here is S theta. Now, what is S theta? S theta, let me write here, is amplitude cosine on the omega plus phase. It is S theta because it depends on amplitude, omega, and phase. And this vector, because there is a vector, is the vector of all the measurement. Okay? So, what I need to compute here, I need to compute 3 terms. Let me compute it. I need to compute S theta with respect to theta 1, which is equal to F theta depending on which is theta 1, amplitude. Okay? Then I need to compute the derivative of S theta with respect to theta 2, which is now the frequency. And the last one is with respect to the phase. Theta 3 is equal to the derivative of the data, the model with respect to the phase. Okay, then, what I do, I aggregate these pieces. Because, according to that, I get the vector of that one. Okay? And so, I don't know if you want to call this one, I don't know if I'm making, but, this is a vector. Okay? So this one, is a vector n times 1. Okay. So that one here is a vector 1 times n multiplied by n times n multiplied by n times 1. Let me put the size here. So this one is 1 times n. This is n times n. And that one is n times 1. Now, since the one in the center is the identity, so it is the inner product between the first vector transpose times the second. Now, I'm going to make that. Clear? I'm going step by step. First time I'm going, slowly. So, what kind of parameters then? Now, what is the derivative of that one with respect to amplitude? Cosine, right? Good. What is the derivative of this one with respect to omega? Then is A, the derivative of cosine, which is sine, And then is the derivative of omega n, which is n. Now, the third one, last one. What is the derivative with respect to phase? Same story. Amplitude, derivative of cosine is minus sine, and then you know the argument remains the same. But now this one is should be a vector. Okay? So to be a vector, just to clarify, I'm making for, I don't want to mess, okay, I write here. Okay. So that means that for the as a vector, when I write a derivative of s theta as a full vector with respect to theta 1, now this one is equal to cosine omega 0 times 0 plus phi. Cosine omega 0 times 1 plus phi. Cosine omega 0 times n minus 1 plus phi. Okay? And the same repeats for the second and the third. Okay? Now I prepare all the elements, okay, which are necessary to calculate this. Okay? Now, let's see, clear? Now let's see how to make it. I told you, you need patience. So I don't know, there is no other way I can allegate, you know, this painful step. Okay? So the first one. So for the first one, you know, so the derivative with respect to the amplitude is cosine. Okay, go back. So the derivative is a cosine. Okay? So then you know what I need to put. I need to put together this vector multiplied by the vector itself. Okay? Placed as an inner product. Inner product is a row vector multiplied by a column vector. Okay? Beyond the word. You know? So it's this by itself. Okay? So now I just renamed, because of the room space, I renamed alpha as omega 0 n plus phi. So you know it's a cos square. But the cos square, you know what is a cos square? Cos square, we know that cos square, sine of cos square divided by n is equal to 1 half. Approximately, when you know the number of samples is very large. So that means that sum of cos square is equal to n divided by 2 times sigma square. This one is the 1 over sigma square is the covariance in the beginning. Okay. Is responsible for that. Then you know I need to compute the second one, which is amplitude and frequency. Now I exactly plug the part, the component that I calculated before. So I have the amplitude, which is a cosine, and the omega, which is a sine, because it's the derivative of cosine. Now, so you know the formula is sine cosine. Okay. Sine cosine, you know, is a sine of 2 alpha, which is here, multiplied by 1 alpha. Okay, it's here. Now, you know, this one is a sum of n sine of 2 alpha. So what does it mean? It means the following, that, you know, it's like to have, let me sketch here, just motivate y is 0. So you know I have the sinusoid, which is this one, and it is multiplied linearly by another scaling term. Okay, so you know, this becomes in the red one. But you know, the area negative and positive, you know, because I'm summing the term. And so that one is, on the mean is 0. So for that reason, you know, that term is approximately 0. Okay? Because I mean, the positive and negative part will simplify each other. Now, when I make amplitude and phase, I aggregate, you know, the two pieces, and now it comes sine of 2 alpha without the scaling term n. That's a 0 as well. Then I take omega, omega, omega. Now this omega, omega, okay, is n squared sine squared. Now I use the trigonometric rule, and this sine squared becomes 1/2 minus 1/2 cosine of 2 times the input. But then this n squared multiplied by cosine, same story, is 0. So this multiplied by that is approximately 0. Then the only that remains out is n squared divided by 2. 2 goes there and it's 0. Now, so I made this one and I put it there. I made this one, I put it there. I made this one, put it there. Okay, so there are still 3 missing. No, am I right? No, 4. I made this one, okay, which is omega. Then I need to compute omega phase. Now you know when I compute omega phase, sine squared becomes a cosine. This times that goes to 0. And to that is approximately 0. It remains a linear dependence. And then a phase. Okay, this one is here. And then I have a phase. So phase is sine squared. Sine squared is, once again, you know, I use the rule that the sum of sine squared is n divided by 2, and then I compute it. Now, you know, everything I made, I put into the Fisher information matrix, you know, which is indicated here. Now, what I notice from the Fisher information matrix, I notice that, remember, this is the amplitude. This is the Fisher information matrix for component that relates to the amplitude, which is the first element. This is the Fisher information matrix on the phase. On the frequency, this is on the phase. And similarly, this is amplitude, frequency, and phase. So what I notice now, I notice that in the Fisher information matrix, the amplitude and frequency are not correlated. Amplitude and phase are not correlated. So, you know, the two sample parameters, okay, they are decoupled, which means the dependency on amplitude and the estimation of the amplitude could be separated from the estimation of frequency and phase. Here, frequency and phase are coupled. If you look at this equation is very, very similar, I would say the same, of the linear regression problem that we solved the last time. In fact, there is a causal relationship between them. Now you know I'm not finished, because I mean, what is the Kramer-Rao bound? Remember, Kramer-Rao bound is equal to the Fisher information matrix inverse.
Sorry, how do we know that omega and the phase are correlated from these values?
Okay.
Because
So what I see here is that, you know, there is the word correlation is wrong. There is a certain dependency between omega and phase, because this term is not 0. In a rigorous way, to claim the interrelation between these two variables, I need to look at the Kramer-Rao bound, which is the inverse of that matrix. So when I compute the inverse of this matrix, which is the one that is calculated here, okay, then from that one I can see that the two set of parameters that are omega and phase here, because of these terms, they are interrelated. They are not decoupled. They are coupled.
We cannot say the same about the amplitudes and
No,
omega
because
the
they're
value
zero.
is zero.
Is zero.
Okay.
So from here I can see that the amplitude, in a rigorous way, I need to look at the Kramer-Rao bound. So that it's also inspectable. I can also check it from the Fisher information matrix, because the matrix, the Fisher information matrix, is block partition. Is here. I have a block here and another block. And since the blocks are oriented along the diagonal, and then when I make the inverse of the block partition matrix that is different from zero only along the diagonal, is the inverse of each of the block. Okay. But if you don't know this rule, the most rigorous way is to look at the Kramer-Rao bound. And from the Kramer-Rao bound, you can immediately say that the out of diagonal terms for omega and phase, so for frequency phase, they are mutually correlated. They are not decoupled.
Okay.
If you think about that, it makes sense. Because estimating the phase means where you start your observation. Okay. So this depends on how big, how broad our thing is a sinusoid. So how longer, how shorter is the period of the sinusoid. So this means that it makes a sort of sense that they are correlated. Okay. But now from this relationship, we got what we were looking for. This is the variance. So along the diagonal, this is the variance of the amplitude. Of course, this plus multiplied by that. Okay? Because from the Kramer-Rao bound, along the diagonal are the variances. Okay, the variances bound. So the variances bound is that for amplitude is 2 times sigma squared divided by n. Okay, so it decreases with the number of samples by 1 over n. So the variance of amplitude of any estimators is larger or equal than 2 times sigma squared divided by n. Okay, that's a bound. Any estimator has the variance that is larger than this. No question of what estimator you are talking about. About the frequency. The variance of the frequency is 24 sigma squared a squared divided by n squared minus 1, which for very large n makes this a simple formula. But if we go back to our problem, going back to the Doppler problem, okay, then I can say that the variance, this variance is the following. So it depends on the inverse of the square of the number of samples. Okay, so from the other problem, my problem is that I can write it is 2L, then it is divided by n cubic, and then it is multiplied by 1 over a squared divided by 2 times sigma squared w, which is what I indicate as sigma to noise ratio. So I have the dependency between the number of samples n and the signal to noise ratio that, remember, it was 20 in the problem. So I know how to choose n. That is the minimum n, because this is the camera amount. Now, I also have a certain variance in the phase. Okay? The variance on the phase depends on this set of factors that for n very large, it depends on 1 over n. So it is a times, which essentially is 4 times divided by n, and then multiplied by 1 over s and r. Okay. Oh. Now, I mean, I can apply to any practical problem. I started with the Doppler. Okay. Now, one comment before you apply to the practical problem we start solving. I make it here because I don't want that stays there. You are recording, right? Okay. So I want that you solve by yourself. Okay. Now that Kramer-Rao says that the variance of omega 0, okay, which is larger than that one. Okay, so it's larger than or equal to Kramer-Rao bound, which is 2 out. Then it is 1 over is a squared divided by 2 times sigma. Okay. Now how much is that? This omega is normalized. It's a normalized omega. So in our problem, okay, we were looking at the signal that was in omega 0 was the frequency? Omegas. One megahertz. Okay? So omega 0 was 1 megahertz. Now if you need to sample this signal, okay, the sampling theorem says that you need to choose delta t or 1 over delta t such that this one, this frequency is fully contained into the sampling capability with that sampling frequency. So, one possibility, just an idea, is that these omega 0, okay, is, we say, can be 1/3, so 1/4 of 1 over delta t. That's one possibility. So, this one is a design choice that we do. Now, if we choose these omega 0 to be 1/4 of 1 over delta t, that means that, in a normalized frequency, we have the true frequency, which is 1 megahertz. Then we put, the normalized, the sampling frequency, F0. So the sampling frequency, which is 1 over delta t. So that is 1 over 2 times delta t. And then I can imagine that my 1 megahertz stays there. This is my design criteria that I used. Which means in a normalized sampling, this is pi, and this is pi alpha. Okay. So that means that, since this one is pi alpha, so it is 1 over delta t is equal to 4 megahertz. Okay? So delta t, is the inverse of 4 megahertz. So delta t is equal to is 1/4 10 to the minus 6. This is delta t. Now, what is this variance of omega. You know, what I need to make it, since this one is adimensional, I need to make it dimensional. And in order to make it dimensional, you know, this omega needs to be scaled by delta t. So what I need to do is to take this omega scaled by delta t. So here it comes a delta t squared. Delta t squared goes multiplied by this n cubic. So delta t squared n squared makes the observation window. And then you get your observation window. So this is the starting point of solid. Now, one additional comment on that. When I look at the Kramer-Rao bound, okay, so the Doppler, I'm not commenting the story of the Doppler anymore, okay? Do it because it's really, you know, important that you get practice on that. And then you will discover that there is a dependency of on the time window, which is time squared, and then there is a dependency of 1 over n, that is another term. But anyway, we need to look at both sides. Now, let's look at the Kramer-Rao bound. Now, when I look at the Kramer-Rao bound, you know, I look at here, this equation. So this equation is a Fisher, right? So, you know, I have a squared divided by 2 sum of, and you know, this is sum from 0 to n minus 1. Depends on where I choose to start my sampling. So here it starts from 0 because I decided that to count my sample starting from 0. Okay. So, you know, let me go back to the example that we did last time. Do you remember the story of samples? Okay, and I made the linear regression. You remember that when I computed the Kramer-Rao bound, it was here. By the way, the formula, you know, if you look at the formula, you will see they are the same. But you know, anyway. And then what we did, we put a 0 in the center. And you know, by putting the 0 in the center, in the sum, it came out that the extreme of the sum, they go symmetrically from minus n half to n half, which is simply taking the signal and refer the 0 to another place. Okay? Now, you know, this is what we did a couple of days ago. Now, can we do similarly here? Well, if I look at the Kramer-Rao bound, you know, the Kramer-Rao bound starts from 0 to n minus 1. And here starts from 0 to n minus 1. Now, this term is different from 0 only because I labeled the samples starting from 0. But what about if my samples are symmetrically generated? As for the line regression, now if the samples are symmetrically generated, this sum is not from 0 to n minus 1, but it is from n half to n half, minus n half to n half. So it means that, you know, if we have a possibility to take the samples and rename it, you know, since it isn't a computer, I mean, I can always do it. So this is my data, okay? And this data is a block in your computer. Now, I mean, you can call this one as sample 0. You can call this one as sample 1. You can call this one as sample 2, right? This is what we did now. But you know, I mean, I can call this one n minus n half. I can refer to this one as minus n half plus 1. That's all. Until I go to the last one, which is here is n minus 1. And in the new representation is n half. So if I act in this way, you know, my sum over there is symmetric. So I'm summing from minus n half to n half. And that sum, that the off diagonal term, this and that, are 0. And this is, you know, exactly what we can do. Now, if I do it this way, this and this are different from 0. This and this is equal to 0. Then what's a common? Is that the frequency and phase are decoupled. Similarly as for linear regression. So this is what you find here. This case is if the phase is known. I don't know. I didn't do that. Sorry, I didn't do that. But so if you do it by yourself, okay, it comes out that the dependency is 0 on the fish on the criminal bound, and this term is a smaller, okay. And so this remains the same, and this is smaller. So the variance on the phase is smaller, but the phase was nuisance. So since the phase is nuisance, in this case, doing this way or not is optional. It's totally arbitrary. If the phase was important, then you must do by counting in this way, which is by counting symmetrically. If the phase is important. If the phase is not important, then you can count as you wish. They might be coupled. Because the phase, as in our problem, was not random. Because we started saying phase is a nuisance. Okay. Are you deaf? You know what to say? Is it clear? You need to study that, you understand, so. Now, I encourage you to look at these 5 lines here. Now, let me explain to you what these are 5 lines say. These 5 lines say the following. The Y frequency and the linear regression are brothers. Are related problems, like two sides of the same coin. When I make a linear regression, okay, so I have a set of points, and then I can make a linear regression. But when I look at the estimation of the frequency of the sinusoid, and looking at the model is cosine omega 0 plus right? And then I have plus noise. Now actually, it is like if we have 2 vectors that are rotating in plane. One vector is rotating in one direction, and the other vector is rotating in the opposite direction. The 2 vectors compound to make a cosine. Okay? You know that, if I need to make a cosine of the phase, arbitrary phase, it is equal to AJ phase plus A minus J phase divided. Okay? So this and that are 2 vectors. Huh? They are rotating because they're changing the phase in the end. Okay? So the angular speed of rotation is omega. So, actually, this is the vector representing one of the 2. So I can take this cosine and write, the vector and the other vector that is rotating in the other direction. They compound, they get, a real one. Now, so if you look at just one vector, okay, so looking just at one vector, now this is a vector that has a length A divided by 2. Is divided by 2 because of the story of summing 2 vectors. So I have a long vector here, and then there is some noise superimposed. So the phase I'm looking is this one. So this is the phase omega 0 n plus phi, which is increasing, but every sample is increasing, okay? And then, superimpose there is a noise. So this angle is omega, is a phase that I measure. So, could be omega 0 plus a certain, plus omega 0 n plus phase plus beta. Beta that depends on the noise. So what I'm saying is the following, that if I look at the problem on the phase only, now the phase is linearly increasing. So since the phase is linearly increasing, if I look at the problem on the phase, so what I can represent is that the phase of xn, the phase of xn is linearly increasing, and and is perturbed by the representation of the noise onto this plane. That is the perturbation due to W. So my goal when I estimate the frequency of a sinusoid is that I need to estimate this linear growing phase. So estimating the linear growing phase is the same of estimating the slope of this curve. And estimating a phase is equivalent to estimate the phase of this growing curve. So this problem is a linear regression problem on phase of x. And this is the reason why the two formula comes the same. Because they are two sides of the same coin. Okay. Now, the last aspect I told you about the problem of the police radar. I want to look at the problem of frequency estimation, which is the Doppler. Then, according to the Doppler, we know what is the speed of the car. But then, perhaps the police wants to know what is the distance. Okay? So the distance is from the time of delay. So let's look at the time of delay there. You see, I'm using the Doppler, the police device as a common problem, which is putting together the frequency estimation in a practical sense and the time of delay estimation. Now I don't discuss about the Doppler. I don't discuss about the camera out. I only illustrate how to estimate a delay. And so if the laser by the police is measuring the delay, so my goal is to measure, the time of delay corresponding to the pulse backscattered by the car. So I have my, my laser here, or my pointer, and I have a car. So, so it takes some time, huh? So from here I can measure the distance. Yeah, it's telling me that I need to stop here. So then this is the model, in this case.